start with a small extension to the previous session. So we're trying to understand the types of state machines. So anybody remembers what are the different types of state machines? You can place in chat window. Let me see. I go to chat. I don't see anyone.
Deterministic and non-deterministic.
Very good. That's nice. Okay. So deterministic and non-deterministic. And do we know the difference between them? So can somebody say what is deterministic and what is non-deterministic?
Deterministic have only one path from one state to another state, and non-deterministic have many paths.
Very right. And this is a very good example. Diagrammatically, not so nice looking diagram, but notional. This is a start and this is an end. And here you can see that there's multiple routes via which you can reach to your end. There's a single route via which you, and you know the most of the problems are of non-deterministic type. So you know, if we are in this real world, we are somewhere here most of the time, you know, and the challenge is to convert them into a realistic machine. So we have to convert non-deterministic state machines, and we should be able to convert them actually to a deterministic state machine, you know. So that's where you come to make it more predictable. So ultimate objective would be to convert a non-deterministic state machine to a deterministic state machine by isolating the other routes which you do not require. And that is where, how do you isolate is the real algorithm, is the real assessment, is the real experience which you will come across based on application. Why we should choose route 1, why we should choose route 2. So evaluating all the routes of algorithm which will lead to a next state of destination is a very challenging engineering work, and that is where you will go and contribute and make some differences, you know. So how do we do that? Depending on so many factors, so many activities. So we'll try to, you know, see if we could take a very simplified example to start with, and then see that if it really fits your ways. Okay. So let me erase this board for a while, and then we'll start again. So I will take a very simple example, and we'll take a code example, a software example, and I'd like to take 2 different examples. So we'll name one of the algorithm as say swapx, and it takes certain pointer handler, say x and into y. So we'll take a very trivial example so that easy to understand, and then you can start correlating with this to other examples as well. Okay. Now, you know, if in this function, you know, I would like to have one of the algorithm. So say I may use, you know, it could be associative method. So I could say star x assigns star x plus y, or even I could have used an XOR logic. Or just get settled on this. And we'd like y to have removed from the recent x modified value from y itself, yet to modified, and that gives us a new value in y. X still is looking for a change, so I apply x here, and we say okay, x goes with itself, which is unmodified, and it takes the newly modified y's value. Something like this could be, you know, one of the notable version in the system. And you know, we can think of a very similar function on the same lines, and I think we should make them as you know, let's think of some other color. Yeah, and yeah, I'll make it a swap y, and then This time we'll have a different idea on swap. So might be I use a temporal methods. I use t assigns to x, and then more of a load and store go, right? So I say star y, then assigns to your, so yeah, x is stored, so x needs a replacement. I assign it to y, and then y copies itself back from the temporary. So more or less good, okay. Seems okay. So these are the two different functions, and we need to understand that ultimate objective of both the algorithm is the same resultant. So whether I use swap x or swap y, the resultant of the number passed in this function is going to be the same, right? So you can think of, that any two numbers which are passing by address. So it's a very good example of you telling passing by address or passing by pointers in C. Whereas in, whatever the values you pass, it's modified by this method or algorithm, and it's returned back to the client or the function callee. Okay. Now the question is, what are those scenarios? What are those cases under which we will start thinking about we can make use of different kinds of swap, right? Let's try to drill down this. Here is where, engineers comes in picture, where, your programming skills for the hardware skills for, so you should know your hardware, you should know your compiler, the code being generated for you. It increases, your ability to take and make meta decisions. All right. So I just want to tear this down on a very, simple, I would say, architecture. And maybe, fundamentally, it may be a good idea to know that how they flow. So let's take one reference architecture. So we'll take a popular Intel x86 architecture. And guys, do you know what do you mean by x86? Why do we use this notion? Anyone?
Microprocessor?
No, when I say x86, it has a different notion. Not only 32-bit, it says the family of 80386 and above. This is a very industrial naming, more of a, style, I would say, is rather than saying 386, 486, 586, D, go to duo, or so and so on, I3, 4, 5. We just say x86, S6. It just refers to all the architecture which is 32-bit and above, and usually compatible from 386 onwards, something like this. Anyway, so now this is important because if you look at an Intel and you have a compiler might generate certain architecture specific code for this, right? So let's try. So let's drill down this expression to something more meaningful in terms of mnemonics, right? And you should know the load and store instructions which will be generated on behalf of the high-level language in C, right? So an assembly section or an assembly section will be a good choice for you to actually look out for the different ways compiler generates the code base for both the algorithms. Okay, so I will just try to do it manually, and then later on, as you start maturing, you start learning about tools, you start learning about some binary utilities. You can start drilling down some more complex algorithms over a period of time. All right. Now let me start with text. So I would say, like move well. Now move well stands for move long. I use AT&T style coding in assembly, where we go from left to right. Most of the other assemblers like MASM, TASM, BASM, NASM are typically which goes from right to left, but AT&T always goes from left to right. That's standard for RISC and CISC, both architectures. So that's why I prefer this. And I will always advocate and advise you guys also to upgrade on this in case if you have some time. Again, I'm not trying here to drill you down to say that everybody should mug up all the mnemonics and instruction, but it's a very good knowledge to have that how an architecture is going to expand the code, because if you have to go at minute level of optimization and make some serious decision about choosing which algorithm or which path to reach a destination is going to be chosen, then you must have this with you. All right. So move L is a move long, and I say, let's say that X, now dollar is a sign as a syntax used for constant, and this goes and moves to some of the architecture specific registers, say eAX, which is an accumulator. And now I'll have something more. I got to perform some kind of an add. So I'll say add as an instruction, and I'll say, let's do $y, which goes with mod eAX. eAX has Y already. So the content now, the content of Y goes to eAX. eAX now again performs a move L, and then you have something like a mod eAX, which pushes the value back to X because X is on left hand side, and that's getting updated. Now the similar lines of the code will flourish here, and you can think like now the ones which is going to be subtracted, so X will go to this and Y gets subtracted from this. So I just replace this with this UP, right? Because X is the last update. Move L is back to now not X but Y. Now same natural process continues. X is same subtraction of things changes only the loaded store. Here you will have sub Y, which is unchanged. But while subtracting, you will be using Y because that's a newly stored value, something like this, guys. Now, if I were to do a similar kind of a job here, things are a little bit different here. You can see on the right-hand side for swap Y, then I'll say something like move L, and then I say, okay, let's see something like, and X moves to eAX, and then let's move L, the eAX register back to temporary, which is a $T, and then I almost do a load and store for the same over here, and it's like now Y has to be assigned to X, so you have to be careful to push Y to eAX, and then instead of T to X, we would have to say that, you can think of, that Y being assigned to X, so Y goes to move eAX, and then eAX assigns back to Y to T. So Y has to go and sit in eAX as effective, and then I have to put T, which has to be uploaded to eAX. So I'll say have $T being moved to eAX and then updated, something like this. So as you can see, there's a huge difference in the way your code is generating based on the algorithm which you're using. And the funny part is that when you pass the value, both of them will end up giving you the same result, right? So from output perspective, if you see an application not having any side reaction, because the result is going to be the same. Hey, he arrived, you arrived, that's it. But there is going to be a significant processing difference, right? The amount of cycles which you're going to consume on the left-hand side is going to be huge. On the right-hand side is going to be reduced. But look at the other way. For example, let's look at, so, this was instruction and the cycles which we're trying to examine as of now, isn't it? So let's put them all together in this highlight. Use a similar color so that we know that this is cycles. Now look at memory stuff. So, like that's also very interesting. So I like to just name this, becomes easy. I'm gonna take this cycles which we're looking at, and now let's talk about a little bit on memory. So if you look at the left-hand side, the memory will be a little bit different because you have two variables, all are integer size. On a 32-bit size is going to be 4 bytes, word size. So roughly you may have a stack being built because of local data, correct? So you may have a stack being built for this. Let's try build a stack frame. And it's 2 of them. So of course, you may have some padding, which is fair enough. Just trying to be a little bit decorative. You know, and on the other side, things, yeah, let's label them, guys. So, you know, like X and Y. So X sits over here, and then you have Y sitting over here on the stack. And we say this is a Y. And then, you know, you can always mention them. They're on top of the stack. So this usually is referred as toss. Remember, I'll be using this term more often in the optimization in future when we talk about C for embedded. So TOS stands for top of the stack, you know, as an optimizer. It means that the compilers uses the stack top or the top of the stack for manipulating or accessing the mostly frequently utilized data, right? So you must have seen that when you build a stack or a pile of stacks of books or anything as such, you want to ensure that, you know, the most recently used books is on top. You can have an easy access to them and put it back. So often, mostly frequently utilized books is well placed on top because that's what I'm reading right now, you know, something like that. And that's the design under which the most of the architecture operate on stack-based architecture. There are some more, you know, a lot of microcontrollers, they don't have their own stack. They share stacks across RAM banks on microcontrollers like PIC and ARM16, and then some Renesas R850 and MIPS, and a lot of architectures, okay? But as of now, you know, you just think like, you know, we are operating on TOS. And now let's also see on the right-hand side, guys, if you look at the top of the stack, on the right-hand side, then things are a little bit different, you know. Let me draw. As you must have guessed, we have more stack than the left-hand side, because here you have a temporary, which is T. So, but yeah, you got to draw them. Let's do that quick, or relatively. But and the bad thing, it doesn't allow me to copy. All right, so this goes the second person of the stack, and then I will have a top of the stack. All right, yeah, okay, bingo. And now I'm gonna just label them again. That let's say we have an X being declared first, and then we have a Y on top. All right, and then we also have T on top, right? And again, that's gonna be my top of the stack. So place it here. This fashion, that's again a task on top of the stack. Or maybe a text, right? So as you can fairly see now, if I had to draw a table of comparison on this, how do I draw a table? Okay, I cannot mimic a table. Let's consolidate this data, and yeah, we'll make a label here, which might be, you know, the algorithms. So we'll place the algorithms on the right, and we'll take the split route for them. I can build this up, guys. I'm gonna just do this here. I'm not using a PPT because, you know, this is an example of how we use storyboards rather than using a static PPT. Of course, we can run some PPT as well, but just trying to be interactive. Now in my text, I'm going to say that we are evaluating as already got. Yeah, here is saying that this is your time, or maybe cycles. Challenge. Cycles. Here, memory. So when I say the algorithm for swap X, this is when I say algorithm for swap Y, I can see what I've been trying to draw out of this is the number of cycles on swap X is like 1, 2, 3. So I'm now talking about atomic instruction. Can somebody say what is atomic instruction, guys? Anyone? You guys are all hardware, right? What do you mean by atomic instruction? No Googling.
Those are the instruction in which we read and write at the same time. Like for a part, if we are using the same variable for multiple purpose.
No. So, see guys, see, atomic instruction means an instruction which cannot be interrupted, right? It usually finishes less than 1.5 cycle or a cycle. That's atomic instruction. Usually, they do not get instructed. So ALE is designed in a way like when you start taking a latch, before you finish that particular cycle, there's no other instruction which is going to run. And sometimes we use micro architecture coding, or we use horizontal barring or decoding in a way that we can combine two or three instructions as a part of microcode that they execute and still they do not get interrupted, right? For scalability in parallel, heavy parallel processing. So it's a very interesting aspects of you trying to increase the overall interrupt latency in the system, that at least there must be a certain instruction which must be completed before and after an interrupt has arrived. So every instruction, like load and store instruction, is a very good example of atomic. For example, move L is a very good example of a load instruction, and that's atomic instruction, and it cannot be interrupted once it starts, right? Yeah. And when you talk about, add, add is again an example of not a single cycle instruction. It may take more than one cycle, but we do some microcoding logic via which, while the addition is going on, you don't get interrupted. But however, what if, you have all these three instructions to be performed at one shot? That may be a huge task. So it's very clear that, when you're writing move L, add, and move L, there's three instruction. So before the instruction and after the processing of instruction, we don't count any disturbance. But what if the interrupts arrive after move L, after add? So there are possibilities of two interrupts arriving at least on one line post these two instructions. So that's the worst case, number of hits these three cycle instructions can have if they are not atomic. They can have more. So, the design is very important from us. And I would say that let's assume as of now that, adder is a half adder and maybe, or a full adder maybe. Yeah. And then, it takes just a 2 cycle operation. So in that case, we are going to sum up 1 plus 2 plus 1 again, that's 4. That multiplies over 3, almost same. Subtraction, same thing. So 4 into 3 is 12 cycle. So I can, at least conclude to some extent that, yeah, swap X cycles are going to be how much it is, 4 into 3, 12 cycles, right? And this is just notional. Again, you run on ARM, you run on MIPS, you run on PowerPC, things will just start changing. So you need to statically derive if you're right, or taking a project where you have multiple hardwares on board and you have an ownership on different kind of product version, so the solution will keep changing from version to version and person to person and system to system, right? So we need to be, aware about this trade-off. And the same thing on the left-hand side, if you say it's a pure load and store operation, it just takes 6 cycles, almost half the time. Now you go for memory. When you see memory on the left-hand side, it's more optimized. It says 4 plus 4 on a 32-bit machine. I can say 8 bytes. And on our counterfeit, we have 12 bytes of memory being consumed. So, at least, if I were to, take some decision, we got some facts now, right? We are very clear about swap X and swap Y, but still, decision is contextual. Now, I cannot say that swap X looks better or swap Y looks very good, because there's a trade-off of time and space. You can see one of the hardest problem which everybody is trying to solve in this world, whether it's Google, whether it's you or me or anybody else, is how to make the complexity of algorithm O of 1. I mean, virtually impossible to achieve is what we're trying to, right? Like, you want to virtually achieve the cheating for death, and that's not going to happen. Similarly, we're trying to achieve something like fail-proof system, and that's never going to happen. You can just make fail-safe. You cannot make fail-proof system. So there's absolutely, state machine will always answer from one state to another by only eliminating options, but it cannot rule out any options in the real world. So we are trying to see that if we can make more and more predictability by experience work in a system, as long as it's alive, it will keep working on. But it can not say that it will never break, So it's a very hard call for all of us to make, whether X goes or Y goes in. But yeah, there is a way to start. At least if if as a developer, as an architect, as a solution guy, if you know that you can break down the problems to this extent, then you have a very good. I mean, don't think that you have to do this manually, guys. There are a hell of a tools which can generate this kind of code. Okay, and a large code. Think of 500,000 lines of source code which you have to debug, and you have been given something like 3 months of cycle to debug this code and see, guys, can we improvise on this? Can we make this some changes? Can we add some more functionality on this? So so it's a hard problem. So you need to use tools to generate an assembly, watch this. So, but you have to start from small, incremental. There's a saying they say keep mixing small. 30 plus 30 ml itself becomes 60, and then 90, and so on. So they say there's a saying called small milate jao and large banate jao in native year, that applies to the software model for incremental development and hardware model for incremental development. So you keep inch by inch, breaking down the problems with algorithm to algorithm, and then evaluate them on a particular architecture, and then try to make some suggestion and see if it is the right fit for you. So just coming back to that, having said enough, swap X and Y. If I have to choose swap X, what are the trade-off? If I have a slow processor, but decent memory is not an issue, then still it's a bad call to use swap X, because you have a slow processor, you have only 1 megahertz, say for example a CPU, and you're running this program which is calling itself for 10,000 times. And versus if you have a very high speed CPU but crunch RAM, then there's a huge problem, right? Because if you have a high speed machine, then it makes sense, but memory is constrained, then probably swap X will be a good fit, because it takes more cycle, but the CPU is pretty good enough to take them up, right? And the memory is the constraint, so I can go for that. Swap Y asks me that, see, if you have a slow processor, but memory is confident enough or liberal enough, I may choose swap Y for that example. Or if both of them doesn't work, then we sit together in the team and decide, hey, is there any way to further optimize this? Can we write algorithm 3? Can we try something? Maybe another mechanism of swap by using bit fields, and it may be more improvised. Can we do that? Something like that. So what are we trying to? What is the overall learning objective of this example, guys? That we are trying to understand that majority of our problem which exist, they are non-deterministic in nature. So I can't say swap X is always predictable and it's always going to take these many cycles on every architecture. Can we say that? I mean, absolutely no. It cannot be. Even though you have written this particular program, there is a context here. I have been very specific to mention Intel x86. I couldn't be saying the same thing with ARM. I couldn't be saying with ARM R architecture or M architecture or A series architecture. I cannot say the same thing for a 50 megahertz CPU versus a 100 megahertz or a 1 gigahertz CPU. There is a huge difference in the way the codes will start changing. It's a kind of a chameleon code which keeps changing in embedded very swiftly and quickly, and without you even noticing them. When you are in a project solving state, you will not have a drill down approach like this, where you will have enough time to go and function by function and then try to understand the history of this source code. Where was this code base from? Did we pick it from the previous architecture? Was it a 8-bit or 16-bit architecture? Oh, you run a Kale, but I'm running a real views, or somebody's running an AVR box. And no, it's a maybe QNX Momentex. So ID keeps changing, architectures keep changing, and it becomes really hard, guys. So that's the sensitivity in embedded application or software engineers. This is the difference between an application programmer and an embedded software engineer programmer. In embedded software programmers, we need to have very good knowledge of at least one or two architectures. We should have a very good knowledge of the way high-level program works. We should be having a very good knowledge of how these programs are influenced by certain compilers for that architecture. We should also be aware about breaking down the compiler-generated codes to our understanding. We should also be aware about the memory policy and allocation techniques used by the architecture and compiler to manipulate the data, and of course, tools via which you can generate these kind of tabular data. So this will help you in at least making a very wise decision. Convinced? Right? Now, so in broad terms, you can think that if I had a state, let's say, let me share. Where is a new share? Okay. Crazy. Oh, metroing. So you can think, that there may be some start, there can be some main, and there would be a situation goal to have some result, and then have not. I'm just trying to draw something which we can diagrammatically represent, guys. I think this is my start. Right. So just to context you, I can think of a main, okay, in C, which is my start, and I may say an exit, which is an end. Okay. Success or something like that. Maybe I'll just be a little bit crude, saying exit with 0 naked value, and then I say, okay, I'll use a swap X. Let's say pass an address of a number, say A, and a number B. I'm just trying to make some case. Say I have an int A assigns 1, and then a B assigns 2 in this case, and I also say swap Y. Let's say I assert A and then comma B. There you go. And then say if something like 1, and then do something like this. Else if 2, and then just check 1, 2, and then say eAge 1. Something like this. Or you can scan and then change it, and so on. Keep going. I'm just trying to give you a snippet. Don't go by huge syntax and other things as of now, guys, because let me formally introduce you embedded C syntaxes. I know everybody is an expert over here, but yeah, No, just keep it here. So, now I'm trying to say that, when you say start as main, and then, you need to have a switch. So you can draw some kind of a diagram. So let's try to do that. Let's see. Okay, all right. So let's have a state. This looks poor. I have to take a free drawing. Okay. So maybe I do something like this, guys. Okay, this is one state. And this transition can be because of one. So I'll say that. You can also use like two. And then both of them will have the same resultant state, which could be swap number. And then from there, you don't do anything except like this. Okay. Not a very strong state machine, but will serve us purpose. All right. Now see that if it is CHS1 and then you have CHS2, okay. And now what I say is, if you have CHS1 and 2, then you have a different function being called there, right? So based on your start input, you have to make a call to 1. This is, I'm going to swap AX. Okay. I think I'm not writing in the right place. Let me Z it. How do I undo? And then, of course, I can say here. So is, and then it goes as 1 and 2. And state of, where you can think X assigns to, maybe A assigns to here to 1, correct? And then you can think of B being assigned to something like this. Okay, there you go. And here you think that have Y, guys, and then this is still the same. Right? And here you have a state where you say that you have actually A assigns to 2 and B assigns 1 here, and then you have a function here, say exit. So okay, looks everything good, and then so despite this is the machine where you have an end, and then you have a start main, start, right? Exit with an end, something like this. So this is a nice way of representing your state machine, that somebody starts the system and then have a choice, and a non-deterministic state machine, because whenever you take CH1, processing power will be more consumed and memory will be reduced. And whenever you take CHS2, then the processing power may be pretty fast. Your pro code may complete quick, but memory consumption will be high. And if there are hundreds and thousands and millions of calls, if you think that we have 10,000 threads which is being created, and if it is a client call from an external system, and you are the service provider for them in the enterprise class embedded softwares, then suddenly this entire idea starts getting complex, and then it becomes vital for you to actually choose one such state machine. So think that if I cross any one of them, for whatever reasons I have chosen to not select them, if I cross them up, then don't you think that we are now actually trying to be deterministic? Here it is not, but here there is no choices. I'm going to hardcode my engine or my software or my SOC to say that, hey, I'm going to go for CH1, whatever, come may, what may. For this situation, this is perfectly fit for me, and I'm up for it. So now I'll always be predictive that A is going to take 15 cycles, whatever cycle, let me take 500 cycles, but I will be aware this route suits me. it doesn't matter, even though it takes 3 days to reach JFK, I will reach like this because it saves me this. You have a boundary under which you have decided to move ahead, right? So we are trying to achieve a conversion of a non-deterministic to a deterministic machine. And that's a very hard problem. Are we agreeing it is not so easy to perform this as it looks here? What do you guys say? Fair enough? Yeah. Yeah. So that's the crux of your system. I have seen people with 20 years, 25 years experience. I have had a chance to, address some of the very senior people who are almost like my dad's age at the time, and people from ISRO work and whatnot. They have been writing Fortran for the last 30 years, and we have to change them to an embedded C++ engineer. And we had a horrible time for 3-4 weeks sitting with them and trying to change them. They're like crazy algorithm writers, but all in no vain. We could achieve some tolerance initially, but yeah, it went on well. So I'm just trying to say you that perspective is very important in embedded, guys. We've just started to give you some context. I do not want to complicate as of now. For the first few, sessions, at least for the first 5 days or 6 days, I want to go a little bit lighter, and then we'll accelerate a little bit.